Okay, second last class, and we got our last class on Thursday, and I'll talk a little bit more about the exam, maybe on Thursday class, so make sure you don't miss it, and we'll talk about the format and maybe give you some information on Thursday, okay? But let's see what else to remind you. Assignment number 4, there's no subsequent programming test to cover that, but for your learning, you may want to take some time, complete that. It's a different problem to deal with. I think it's an interesting problem to deal with. Anyway, if you got any question, reach out to me. And for the makeup lecture, that'll be the last one for your programming test too. The plan would be to release them maybe after the Thursday class. It wouldn't be much. It's just to do a little bit about binary search tree deletion and also cover some operation on the heap, which we'll cover a bit today. But anyway, I'll reach out to you. So you got enough time, definitely, to catch up with all the makeup lecture and also the material. And there's another bonus opportunity for you guys, optional. If you want to do the course evaluation, please go ahead. And then if the response rate reach the threshold, which I mentioned, you guys can definitely get some bonus. I'll be more than happy to show my appreciation for your participation. And then for office hour, I still got tomorrow and also Thursday this week. So starting from next week, you guys will be busy with other exams, but I'll try to also make some office hour available. If you want to speak to me about the course material, you're welcome to. And also, I plan to maybe schedule 1 or 2 maybe Zoom session to also review, Q&A. But for that one there, I can reach out to you maybe a little bit closer to the exam. There's no point to do that too early. You guys need some time to study and also digest the material. For that one, I'll reach out to you on e-class. All right, any question about the course? Yes?
Are we going to, during the exam week, going to have
for the TA, they might have to focus a little bit more on the grading, but I'll make myself available. So if you somehow you cannot make it to my office hour, just reach out. I can make some time for you. Okay? Yeah. I'll be on campus almost every weekday anyway. So you guys, if you want to drop by, just let me know so we can talk. Okay. All right, so let's do a quick recap about what we said last time. So last time, we basically started with the idea about binary search tree. And there are basically 2 properties you want to really study for the binary search tree. One would be the so-called search property, and the other one, the sorting property. And the search property is really about given any internal nodes, the key values on every node in the left subtree must be strictly less than the key value for the root, and symmetrically, every node in the right subtree must have their key value strictly larger than that. As simple as that. And it's a recursive property, meaning that you have to check this property here on every internal node in the tree. Okay? But the more efficient way of checking if a tree is actually a binary search tree is by using a sorting property. Basically, you do some in-order traversal and try to see if this resulting key in the sequence is sorted in the ascending order. Right? That's another way to check it. Right? We discussed a lot in details about the sorting property, especially when you study this for the exam. I want you to focus on about seeing the exact correspondence between the linear sequence there and see which part of the sequence will really correspond to, for example, this part of the subtree. Right? That's always kind of talked about last time from scratch. That's something you want to pay attention to. And also, we try to compare the way we kind of try to combine the sequences together with the concatenation operation in quicksort. Right? It's another insightful comparison you can do. Okay? So search property and sorting property about binary search tree. And then we move on, talk about some exercises, just about if you somehow modify one of the node key value, should the resulting tree still be binary search tree? And the easiest way for you to check it is to see if the resulting sequence by in-order traversal will still be sorted. That's the easiest way. And as we will see a little bit today, it is very important for you guys to identify, let's say this is the node we are trying to change, right? Change that to 69. We mentioned about something so-called predecessor and also successor in the sorting sequence, right? In the sequence, it's very easy to see either before or after. However, in the tree, you will actually have to identify the predecessor and also successor. The way to see that is, think about what you would do in the in-order traversal. If you do the in-order traversal, you would say, for example, 54, 65, and then 69, and then 80. So this will be predecessor, this will be successor, right? That's something you want to keep in mind. And today, we'll talk about how you can do searching and insertion for binary search tree. So this idea about predecessor and successor will actually come handy and also useful. As part of your makeup lecture, which I will release on Thursday, you will have to study about how to do deletion from binary search tree. And there will be 4 different cases you have to worry about deletion. And one of the insights you really want to keep is about this predecessor and successor idea. Okay, just keep in mind. Okay, so when you study for the exam, definitely pay attention to these 2, like a different predecessor and successor. All right, so this is the example we did where if you modify the node value, it's not going to be binary search tree anymore because the resulting sequence is not sorted anymore. Okay. And we talk about this general structure about the binary search tree. So we identify 3 nodes. We got N1, left child, N2, the root, and also N3, right child, and also N4, right? We talk about the in order sequence. Especially, we talk about what could be the minimum right here, and what could be the maximum right here. And also, if you think about N2 and N3, relative to P over here, right? N2 is the maximum value that is strictly less than P, as you can see right here. And also N3 is the minimum value that is strictly larger than P, as you can see right here. Right? So these are the 2 additional insights we also made last time. You want to also make sure you feel comfortable about these kind of concept over here. Any questions? Good. And then we talk about how to implement the binary search tree node. In some ways, it's a little bit more straightforward than just general tree because we only got left and right references. We don't have SLL node. In some ways, it's simpler, which is good. So for the exam, I might either give you maybe some starter code in BST node, or I might give you maybe the tree node. So you got to see which one is given. So you got to maybe implement something simple accordingly. I'll talk a little bit more about the format for the exam on Thursday. So don't worry. Well, I'll talk about it. And then we talk about how you can use a different constructor to create either external nodes or internal nodes, right? That's something we spoke about as well. And we talk about how you can implement in order traversal. Either you got to go to both left and right if they exist. And go to left subtree, go to right subtree, and go with this order. Left subtree followed by the root and followed by right subtree, right? So that's the in order traversal. And we also try to trace this code together. So you create, so for example, 1, 2, 3 internal nodes, and also 1, 2, 3, 4 external nodes. 1, 2, 3, 4, right? And so these are the lines where you try to set the child and parent references as we traced last time. And eventually, when you try to do the in order traversal, it's going to go for this, followed by that, followed by that. Oh, let me say it again. This, followed by this, right? And then that. So that finished the left half. And then this, followed by this, followed by that, right? So you see exactly the sequence right here. Okay? So that's the last thing we spoke about last Thursday. Any question? So the plan today, we want to dive into the last bits about binary search tree. We want to see how we can do searching and insertion. And these 2 operations are closely related. So once we understand about searching, insertion is very straightforward. Okay, let's spend more time on the searching. Okay. All right, let's see here. Yep. All right, let's now see the slides. You will start with slide number 9. Okay. So let's say we're given a binary search tree. And then we want to somehow search for a particular key, because key is used for searching purpose. So in some ways, it's more like a decision tree because of binary tree, right? You remember one of the applications we spoke about for binary tree is about making decision, either yes or no. In this case, either left or right. And let's now try to learn about searching without seeing the code. Let's learn about it from example. Okay. And you guys can make a very, very quick judgment about whether this input tree here is a binary search tree. Right? You can make that judgment very easily. Just do it in order traversal to see this in the ascending order. Right? I can tell you it is. Right? You can do that also when you study for the exam. Let's say we want to give you, there are only 2 possible scenarios for the search. Either the search was successful or it was not successful, only these 2 cases. But these two cases have some subtle differences about what's being returned. Let's talk about them one by one. Let's say, first case, we want to search for 65. Apparently, 65 is right here. So that should be a successful search. Okay? That's exactly what's going to happen. Okay? So here we got 65 over here that we want to search for that. Oh, just remember, this is a key, right? And we're omitting the details about the data value for the entry, right? Because we only talk about search right here. So what I do is I start with the root right here. And then I know that 65 is actually larger than 44. That means I should go to the right, right? So by going to the right, I'm saying we effectively eliminates the left-hand side, the left subtree here from the search space. Pretty much like a binary search, in which case we eliminate the left half of the array. So think about here, what we're doing is eliminates this subtree because all the key values there are guaranteed to be less than 44, in which case it's not going to be useful for searching for 65. So we can safely disregard them. Less than 44. Okay, we can eliminate them from the search space. And one thing I want to pose to you as a question over here. From this particular example, it looks like we are basically eliminating about half of the search space. We start with the whole tree. It looks like this half and this half are roughly the same, and we are eliminating the half. However, is this always the case for binary search tree? For binary search on a sorted array, it is always the case because we find the middle way, the middle point. However, for binary search tree, I can tell you right away, it may not be the case always. Keep that in mind. And we're going to see the exact details a little bit later. So I'll pose a question here you can think about. How large is this subtree? Should it be n over 2, like a binary search on a sorted array? Or it might be very small, just like a constant, which means we haven't really eliminated much from the search space, right? So this is like a reflection question you want to think about, right? I'll highlight it, and you will find the answer very soon together. Okay? All right, let's move on. So we basically go to the right-hand side, and then we now compare 88 against 65. And we know that 65 is actually strictly less than 88, so we'll go to the left. There we go. And then we are lucky, we have found it right here. So this is a successful search, in which case we return the node storing the key value 65. And this node is actually an internal node. Okay, I'll write it down. So there are two cases for binary search. I'll summarize the result for you. So whenever you want to do searching on the binary search tree, so there are two cases. Case number one, which we just observed, will be successful search. In which case, we simply return, okay, Rn standing for return. We simply return the internal nodes storing the matching key value. So this is the simpler case for us to digest, right? This one's pretty easy, but it's good to warm up a little bit. You either go to left or right each time until you find the key. And in this case, we find the internal nodes that store 65. And we're just going to return it. Return this internal node. All right, any question about case number one? Okay. Let's see case number two, which requires a little bit more insight. Okay. Case number two here, let's say we are trying to find out the key 68. Let's double check. You can double check as well. There's no 68 in the tree. No. So what should we return? Since you cannot return any internal nodes matching 68, So obviously, you should return some external nodes. But which external node should you return? You got so many. Should I return this one here, this one here, this one here, or this one here, right? Logically, which one should I return? The answer is you should really return the external nodes that will somehow put this 60A in the right place as far as the search property is concerned, or as far as the sorting property is concerned. That's something I want to mention up front. But let's see exactly what I meant. Let's still do the normal searching, like how we did it before. So I'm going to say I start with 44 over here. Okay, I'm going to do a little bit faster for the searching. Since I'm searching for 68, right? Just remind you, we are searching for 68, right? 68 is larger than 44, go to the right. 68 is less than 88, go to the left. 68 is larger than 65, go to the right. 68 less than 82, go to the left. And 68 less than 76, we go to the left. And now, we basically reach an external node right here. All right, so once again. And this is the external node we're going to return as a result for unsuccessful search. That's a part one of the story. Okay, let me write it down first. So this is basically the return. We're going to return this external node. However, I want to say more about this external node. Just one moment. Okay, so we talk about case number 2 for searching, right? Unsuccessful. Unsuccessful search, in which case we're going to return some external nodes. However, what's exactly the range of key value for this external node? That's something we want to find out. Okay. Now, I want you to think about the following. Okay, I'll make it a little bit lighter for you. That's also how you should think about it. Why don't we say, since we know this external node somehow belongs to this particular subtree, for example, right? It's part of it. Why don't we say, let's try to do some in-order traversal just for this particular subtree. Let's start with that, okay? So let's say I'm going to give you the range right here. Okay, right here. And then let's call this one here EXT. All right, what's going to be the in-order traversal if you want to do on this particular subtree, right? Let's write it out. So let me put a star over here, okay? And then I will put a star right here. In order traversal, okay? Would you agree? It should be, oh, let's only worry about this particular external node. For other external node, we don't worry, okay? Just make it a little bit simpler, okay? So we're going to go for 54. Followed by 65, and followed by this external nodes, and followed by 76, and then followed by 80, and then followed by 82, and so on, right? There may be something come before. Okay, so far? I'm just doing it in order traversal so we can see exactly what the range is for that particular sorting. Okay? Now, what I want you to do is, for this external node that we return right here, what's its predecessor? 65. Okay, so this one, let me remind you, that's what we call the predecessor. And the 76 over there is the successor, which I'm going to highlight here. Okay? This one here will be the successor. This one tells you this return external node, we can set to it any key value that's in between the predecessor and successor, so that the sequence remain to be sorted. It's a very important insight into this. I'm going to write it down. Okay? So what you really want to understand is for this particular external nodes, its key can be set between the predecessor 65 and a successor 76. And to make it a little bit more mathematical, I'll put it here. Return the external nodes. Let's say the key value for this external nodes should be between 65 and also 76. Okay, it's very important conclusion from here. Okay, I'll pause for one moment and see if you got any question here. Let me recap first, if you, in case you are still kind of processing. Okay, we talk about searching, and there are only two cases. Either it is successful, in which case we return the internal nodes containing the matching key, which is straightforward. If the search is not successful, in which case we find out where is the right spot for this particular key we're looking for, which doesn't exist. Later on, we're going to see that whenever you want to insert, let's say, a new entry with a particular key into the tree, if the key doesn't really exist, this will be where we're going to insert the node into. So that's why I'm mentioning that. For now, we're just searching. We're not creating any new node. But when we get to the insertion, which will come very soon, there will be just one more step to really convert that external node into internal node. And then we are done for the insertion. Okay? But the most important thing for you to remember is, in order to see what will be the value that's valid for this particular external nodes, you want to consider its predecessor and successor based on the in-order traversal. Okay? All right, any question? All right, think about it. I think it's a very insightful thinking, into the tree. Okay. Question? Yes, Jennifer.
Specific to the in order?
Yeah.
So I can't do pre-order or like.
Yeah, because since we're talking about binary search tree, right? If you do pre-order or post-order, it wouldn't give you your sorted sequence, would it?
Oh, right.
Right, exactly. So that's why we talk about in order. Because in order go exactly left subtree, followed by root and right subtree. That will give you a nice sorted order, right? That's why. Yeah. Of course, if you talk about pre-order and post-order for binary search tree, it wouldn't give you a nice sequence like that, right? Okay. So guys, let me add one more comment over here, which will help for later insertion. Okay. Let me say one more thing. So here, So here for this particular external node, let me say star star. Okay. I'll put here. Star star. For a subsequent insertion, this external nodes, the one I'm returning right here, can be set with a key value such that key value k, and k can just be in between the predecessor and successor, right? 65 and also 76. And we're going to revisit this particular point in just one moment. Very soon. Okay. Okay, so that's about searching. And then the next point is, let's look at some code running. Okay, just kind of emphasize the point once more. And we'll look at some code about how you can define the searching. So this is another test case, which also on the lecture side, you can take a look. And this part over here, we have done it last time. So this part over here is just, this part here is just about setting up the nodes and setting up the parent and child references, right? So for this part here, we can skip the tracing since we did it last time. So the result from this block over here is we got this node, and this node. It's a binary search tree because we got 21, 28, 35 sorted. And we got 4 external nodes, 1, 2, 3, and 4. Let me now put the references, okay? So we got N28, N21, N35, right? N28, N21, and also N35, right? So these are the 3 internal nodes. And also we got 4 external nodes. 1, 2, 3, 4. This is external nodes number 1, external nodes number 2, external nodes number 3, also external nodes number 4, right? And I'm omitting about parent and child references, right? That's that one you know from last time. Okay, let's focus more on how the binary search is gonna return based on what we learned from the previous page. Okay, I'm gonna look at 2 lines. You can look at other lines yourself as well as exercise. The first line to look at would be this one here. And the second line would be right here. Okay, it will nicely illustrate again. This one here is going to be a successful search because we say that we're going to start with N28, start with the root right here. And then we're going to search for 21. Okay, that's what we do. And this one here, we start with the root as well, but we're going to search for 33, which doesn't exist. Okay, let's see what's going to be returned. Let's see. So let's do the first one. We're going to say we start with N28 and then search for 21. So start with this particular node here, and then you can see that 21 is actually less than 28. So that means we should go to the left, right here. And then as soon as we get here, we can see that 21 equals 21. We have found it, right? So we're going to return just this node. This is node we're going to return. So that's why you will see that return value is simply N21, exactly here, aliasing. Right? We just emphasize the point, reinforce, revisit what we said earlier. All right, so that's the first one. What about the second one? Let's say we still start with the root, but we want to search for 33, which we know is going to return some external nodes. But which one is it going to return? It turns out it's going to return external node number 3. But let's see exactly how. So we still start with here, right? We start with N28, and then we look for 33. 33 is strictly larger than 28. So we should go to the right, right here. And then we compare 33 with 35. So 33 strictly less than 35. So we should really go to the left. And then we reach the base case, like external nodes. In which case, we're going to return just this node right here. So that's why you will see external node number 3 being returned. All right? Very nicely correspond to what we said earlier in the page. But now we see that in the Java context. And let me emphasize again over here. If you look at external node number 3 that's being returned over here, that one there, its key value should be in between its predecessor and successor, right? What's going to be the predecessor and successor? Let's now see the in order sequence once more. So that's the easiest way for you to really see. Okay, let's now talk about in order traversal. In order traversal over here. Okay, so we start with external node number 1, and then we go for 21. And we go for external node number 2, and then we go for 28, external node number 3, go for 35, and then we go for external node number 4. Right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right? And this one is being returned. So you can see external node number 3 is right here. What can be the key value that we store in this node? It can be just in between the predecessor and successor. As you can see, this is the predecessor. And this one here is the successor. Right? Let's identify them also in the tree. As far as this node is concerned, you can see that predecessor is 28. Predecessor. And then successor is 35 right here. right? All right, any question? Okay, good. So far we basically talk about what should be returned in the either successful or unsuccessful searches for binary search. And the next one is talk about running time. Okay, how efficient is the search? The answer right away will be, it's not necessarily log n. It may not be as efficient as like a binary search on a sorted array, but we're gonna explore how exactly. Okay, let's now talk about the running time. All right, before running time discussion, why don't we take a look at the code here, right? Let's understand the code structure, which is kind of worth our attention. So we talk about this search method here called search, right? And then that one there is going to return some BST node. And this BST node here can either be external or internal, right? Depending on whether it's successful or unsuccessful. Okay, let's make a note right away. This could be either external or internal, depending on whether the search is unsuccessful or successful. And the parameters or the input we take is the root somewhere and also the key we're searching for. Okay, let's now make a note. So the P here is the root in some subtree, and also the K here is the key to search. All right, so let's understand the header first. And there are 4 different cases to consider. Okay, they're not too bad. They correspond to exactly what we just said. Okay, let's go one by one. If the current node we are looking at is already external, for example, if you look before, if the node we are looking at is already here, unsuccessful, just return the external nodes, right? So that one there tells you if that's external, in that way, it's just going to return the current node P, which is external node. Okay, unsuccessful. And the second case is else if it is not external, must be internal. And we also got some matching key. That means successful search. And the P here got to be internal nodes. And this one corresponds to, for example, when we were looking for, let's say 21 here, right? Just return that internal node with the matching key. So these are the two like a base cases that we can return right away. Otherwise, we will have to recur on the tree for as deep as necessary. Okay, that's where the running time is going to get a little bit trickier to calculate, but it's not too bad, right? So let's understand about these two branches. So we got recursive case number 1. Also, we got recursive case number 2, right? They're pretty straightforward in the sense that if the key we're looking for is less than, then we go to the left. If the key is larger than, in that way, we go to the right. Very straightforward, right? And of course, for both of them, we're going to call the same method for recursive call, right? Search. Okay. So the code structure itself is not too bad, right? So you can kind of understand that. Very similar to binary search on the array. So what we need to work out is how many levels should we really go down for the recursive call? That's really what's going to dominate the running time. Okay, let's now abstract that into some diagram here. Let's now compare. Oh, sorry. Let me make a little bit more space for myself. Let's say this is my binary search tree in general, right? Let's say I'm now at level I, somewhere in the middle. Okay, let's say I here, and then, so let's say I'm now in level I, and then the current node I'm looking at is P. So now based on the P value, let's say I don't really have the two base cases here. Let's say I kind of don't have them satisfied. Now I should either go to the left or I should go to the right. What's the running time for one level down? If I'm now in level I, in order for me to get to level I plus 1, what will be the work involved? That's the thing we want to work out. Okay, let's now take a look. So if I want to go down, oh, beg your pardon. if we want to go down one level to level I plus 1. Okay, let's call that over here level I plus 1. Right? Let's say we go to the left, let's say, okay? What we do is we simply go to the left, right? Right here. What's really involved over here? If we go to the left, that means we go for this particular branch. If you, well, remember we count the primitive operation, right, from before. Comparison, and also we got to go to the left. Basically 2 things, right? So what's involved is, number 1, we have to compare the key value we are looking for versus the key of the current node P. Comparison, less than or greater than, right? Either way. And number 2, once we decide whether we should go to the left or go to the right, we have to say get left or get right, which is just a reference, right? Either get left or get right. Either, but not both. However, both of them are constant operation. Agree? They are not complicated. So overall, if you want to move one level down, it will just be bigger of 1. Let's now compare this a little bit with how we work out the merge sort algorithm running time. We kind of said, you go from the original list, that's kind of n size. How many levels would it take for you to split the list all the way down to a singleton list? We work out how many levels are there. And then we work out for each level, what's the running time for the merge. And we kind of multiply them together. We do something very similar over here. We know that in order to do search on the binary search, when we go from one level down, we have to involve constant time operation. But another question is, how many levels should we go down in the worst case? That's the question. How many levels should we go down? Should it be log n necessarily? Or should it be n? Which sounds very expensive. Is there a more accurate measure for us to mention here? That's an important question here. Okay? Let me give you guys a little bit hints before I tell you the answer, right? So if you recall back in the lecture where we talk about binary tree, right? We talk about different bounds for the binary tree measure. We'll talk about either n, the number of nodes, or what's the other measure? H, the height. This is where we can use the height as an accurate measure. So the number of levels you may have to go down all the way to the bottom will be just the h. But the h itself has some lower bound, also has some higher bound. All right? So that's something we're going to see. Okay, so there are 3 ways to express this running time. Okay? Whenever you go down one level, it's going to require big of 1. But how many levels should we go down? Exactly h. So the answer will be the most accurate one. I'll say answer number 1 is going to be big O of h. So this is the most accurate bound on the search, just about h, depending on how high the tree is. So this is what we call a tight and also accurate bound. Tight and accurate. Okay, number 1. But we can say a little bit more. Given that it's h, we know what's the lower bound and what's the upper bound for the heights, right? And there's something I want you guys to maybe revisit just for a few minutes, maybe before before Thursday's lecture. Okay, I'll put it here. You may actually want to revisit one of the previous slides about the bounds. So revisit, given n nodes, given n nodes. And we know that the height should be in between 2 numbers over here. And I want you to go back there to see what exactly are those 2 numbers. I think that'll be also useful as a revisit for your exam, right? But I'm going to mention the asymptotic bounds anyway, right now, right? It's more like approximation, okay? So for answer number 2, we can say that the best case for a search is log n, because we know that the lower bound is about log n. big O of log n. And this one is what we call the best case or lower bound. Okay? And then another way to say that would be, what's the worst case? That would be basically the upper bound right here. So that would be big O of n. And that one there is going to be what we call the worst case for the search, or you can say that's an upper bound for the search. Oh, okay, recap. When we are trying to work out the running time for the search on a binary search tree, abstractly speaking, you want to think about whenever we go down one level by going to the left or to the right, it's going to involve some comparison and some attribute access to the left or the right. It's going to be constant time every time go down one level. But how many levels should we go down maximum? It depends on the height of the tree. So that's why that's the most accurate bound for the search. However, the height itself may have some lower bound and upper bound depending on how the tree is structured. That's something we'll see as well. Okay, it can be either log n or n, depends. All right, any question about this? Yes?
If you choose the median as the root, can you ensure that you always have like a...
Good question here. Well, you might be thinking a little bit more like a pivot, right? Like a quick sort. Put it this way. Depends on how you actually construct a binary search tree or also how you do the insertion deletion. The tree itself may not have the high being log n. So it's not just about choosing the median because you don't necessarily know about all the value you want to put into the tree at one go. You may want to go gradual insertion or deletion, right? Which I'll mention a little bit later. So it's kind of beyond the scope for this course, but I'll mention very briefly. So for binary search tree itself, we kind of will identify to see when it kind of become unbalanced. So you got a height that's really high, like a linear. In 3101, like a subsequent course to this one here, we'll learn about as soon as you identify that your tree becomes unbalanced, there's got to be some repair operation you're going to do. It's something called rotation, which we don't cover in this course, but maybe in 3101. Okay. Yeah. All right, good. Okay, let me see. Okay, guys, how about we do one more page of a comparison, and then we'll take a short break. Okay, just one more. I think the next page is going to clarify things even more. I want you to look at these two trees right here. Okay, these two. Can you just spend about 30 seconds, oh, how about 30 seconds, convince yourself each tree on the left and on the right, they are both binary search tree. Okay? And I'm pretty sure what you're now calculating in your mind is to do in order traversal, right? To see if that's sorted sequence. If you're doing that, definitely on the right track. Okay? So they are both binary search tree. Yeah, you can also verify maybe after class as well. But I can take my word for that. However, we call this tree over here on the left balanced. But we call this one here unbalanced. We'll define exactly what we really meant by balance versus unbalanced a little bit later today. There's some mathematical property we're going to study, but we'll get there a little bit later. So let me just give you some intuition. So this is called a balanced binary search tree. And this one here is what we call unbalanced. Okay. And then, first of all, both of them are binary search tree. So let me call this one binary search tree number 1 and binary search tree number 2. Okay. And both of them, if you do the in order traversal, you're going to get exactly this linear sequence. Okay, you can also double check. You can take my word for that for now. Okay, I'm going to write it down here. So if you do the in order traversal on binary search tree number 1, it's going to give you just the same order as the in order traversal of binary search tree number 2 on the right. And the order is going to be exactly just the array A that I have over here. Okay? And by the way, the equality here is not really assignment, just about mathematical equality. The contents are the same. Okay? I just want to show to you, even though the in-order traversal result is the same, but the actual tree structure is actually very different. That's the main point. Okay? But I'll dive a little bit deeper into it. And let's do a little bit more analysis here. When we talk about binary search tree, number 1 here, the number of nodes, if you count, is going to be 15. Okay, just 15. You can take my word for that. And what is the height of the tree? What is that? Anybody? What's the height for this tree? That should be the log n. Well, that's what we're going to conclude. But what about exact number? What's the height? 5. Okay, good. Okay, maximum depth, right, of the descendants of the root. So if you try to count over here, so you got 1, 2, 3, 4, 5. Maximum. All right. So the height over here would be just equal to 5, and roughly big O of log n. Roughly. Okay. On the other hand, if you look at the right-hand side, the number of nodes is the same. But now we're looking at upper bound for the heights. And that one, the height is about, okay, you can see that over here. So 1, okay, let's see here. 1, oh, sorry, don't count external nodes. 1, 2, 3, 4, 5, 6, 7. 7. And it's about n over 2, which is log, oh, sorry, not log, beg your pardon, big O of n. That's the heights, okay? So we're talking about logarithmic heights and also linear heights, these two. And let's now do some very important comparison. Let's say I'm trying to do a search on either case. And for each search, I'm going to see the corresponding search on the linear sequence over here. And then we're going to see exactly the following. For one of them, the search is going to correspond to a binary search on the sorted array. The other one is going to correspond to a linear search on the sorted array. That's a very important comparison to make, but let's see exactly. Okay. So let's say for the binary search number 1, let's say I'm trying to search for 80. Okay, let's say I'm searching for that, right? And for that one there, let me just wipe this out. Let me do it from scratch again. What's going to happen is, so I know that I start from here. 80 is larger than that. I'm going this way. So that means I start with 44 over here, and then I'll go to the right-hand side. And then identify 88 over here. 88 is about here. And then 80 is actually less than that, so I should really go to the left. So I essentially go to this part over here. And then I got my 65, which is about here. And then I search for 80, so that should be larger than that. So I basically go for this part over here. And then I got 82. And then that one there is actually going to go to the left. And then I got 76, and that one there should really go to 80, right? So basically, go to here. And then I found it, right here, roughly speaking. So you can see the way I'm visualizing it, it's just like a binary search on the sorted array, like how we did it before. You just narrow down the search space about a half each time. Exactly, right? So this one tells you, when I perform the search on this particular balanced binary search tree, it corresponds to a binary search on a sorted array, which is log n. Number 1. Okay, let me write it down first. So searching 80 on the binary search number 1 is just like performing a binary search on the sorted array A. So this is a very important insight, number one. Log n. Let's now try to do a similar search, but on the right-hand side, BST2. That one there is not going to be that efficient, and we'll see exactly how bad it is. And for that one there, let me again try to, show to you. Okay. So let's see here. We are trying to search for 97. Okay. So for 97, larger than 54, go to the right. Larger than 65, go to the right. Larger than 76, go to the right. Larger than 80, go to the right. Larger than that, go to the right. Larger than that, go to the right. Larger than that, go to the right. And we'll get here. Right? That's actually how we go. And let's see how that corresponds to the array. So start with 54. And then we go to 65. And then we go to 76. Go to 80. And then we go to 82. We go to 88. We go to 93. And we go to 97. How does that look to you? Linear search. We're basically like writing a loop and go all the way from left to right until we find it. There's no like a binary search, any kind of pattern there, right? So that one tells you whenever you when you do a search on a binary search tree, it's not necessarily going to correspond to a binary search always. It might just correspond to some linear search. Okay. So for that one there, I'm going to say the conclusion here. So searching 97 on BST number 2 is also a binary search, but because of its shape, it's just like performing a linear search. A linear search on A. Right? Linear search, which will be linear. All right, recap, and then we'll take a short break. When you do a search on a binary search tree, it might just correspond to either a binary search on the corresponding in order sequence, or it might correspond to a linear search on the corresponding in order sequence. It depends on how balanced the binary search tree is. And after the break, very shortly, we're going to see exactly how to define what we really mean by tree being balanced. There's some mathematical property we're going to study. All right? All right, if no further question, why don't we take a short break by taking attendance, please? Okay, so the last bits about this binary search tree lecture, let's talk about insertion very quickly, right? So before the break, we already finished the slides about searching. Example is running time. Okay. Oh, so when you get to slide number 14, right, you want to pay more attention to the table there down at the bottom here. So that one there really summarizes about the different cases for binary search. For the search on the binary search tree. Okay, take a look at that table. Everything has been covered, but it's a nice way to summarize from a different angle. And we're going to talk about insertion right now. Okay, you can look at the slide for the textual definition, but I'm just going to illustrate to you exactly how this insertion will work. Basically, insertion is almost like a searching, almost like. As soon as you get a return node from the searching, either internal or external, you're going to do just one little step further to complete the insertion. That's basically what we're going to see, right? Let's now do example. And then you'll see the slide as well for the more textual description. Okay? So let's talk about case number 1 and case number 2. So now if you want to insert a new entry, so with some key value here, and also some data value here. So if you when you do the searching, you only use a key value. You don't use the data value. Okay? So what we do is think about this 28 over here is a key value that we want to use for searching. And this string value here, assuming that it's a string value, string data we are storing. Get a value. And similarly, you can think about the 68 over here is also the key value we're searching for. Let's do case number 1 first. All right, so for the key, let's now do a little bit speed up search. So 28 is less than 44, so we go to the left. 28 larger than 17, so go to the right. 28 less than 32, so go to the left. And we have found it. as far as the searching is concerned, we return this particular internal nodes, right? So let's say this node that's being returned is n. Okay? So step number 1, you basically search for 28 and return internal nodes, let's say n, right? That's being returned, like objects. Once the node got returned, the 28 is good, but now you're going to make sure the data is set to this particular value, suyang, for example, right? So you may just want to do one little step to say n, that's a return internal nodes, dot set elements. And then we're going to set this particular element to be suyang. That's it for insertion, right? For insertion, if the key of the entry you're trying to insert already exists, you just replace the data value. That's a common practice. What if the key for the new entry doesn't exist? Well, we'll see. Okay? Let's say now we are trying to search for 68 for insertion. So 68 is larger than 44, so we go to the right. 68 less than 88, go to the left. 68 larger than 65, go to the right. 68 less than 82, go to the left. 68 less than 76, go to the left. So we basically end up having to return this external nodes as far as searching is concerned, right? And let's say this one here, let's call that external, no, EXT, let's say. That's a reference we return. Okay? So number 1, you search 68 and return external node EXT. Okay, that's step number 1. And step number 2, I'm going to put it here. You're going to somehow convert that external node into an internal nodes, which is something we actually saw earlier before, if you remember, when we do that mathematical induction, right, on that proper binary tree. We did something very similar. You can revisit that point here, okay? But we're just doing that again. And for step number 2, we're going to convert EXT, the return node over here, into an internal node. Visually speaking, EXT is a little bit like this. And convert that into an internal node, which will look like something like this. And that internal node should really store 68 and also store the data value UNAM over here. And then that one there will contain 2 external nodes as the children. That's the extra step you got to do. So once you got external node return, you know that the key value there is actually properly set up. Again, you can look at the predecessor and successor, right? So for this one here, predecessor is right here. And the successor is right here. Right? So we just make sure the value there, 68, is in between 65 and also 76. Exactly, right? And then you just got to convert. Okay? That's insertion. 2 cases. And what about running time? Basically, the first step here for both cases is going to be about searching. So that searching part dominates the running time, which is log n. Actually, sorry, it's big of h, which can be log n in the best case or can be n in the worst case. And the second step over here for both cases is just about some constant time operation of creating objects. So that one is not going to change anything. So the insertion here is dominated by searching, which is big of h. Okay, so I can write some remark here for you. Okay, insertion over here. The runtime is dominated by searching, which we know the most accurate for saying that is big O of h. All right. the last bit about this binary search tree lecture is about deletion. And that will be part of the makeup lecture I'm going to release on Thursday, right? You guys can take a look. So for deletion of the binary search tree, that one is a little bit more sophisticated. You will have to consider like 4 different cases, right? For insertion, you can also try some code exercise. You can take a look at that. And for deletion, we got different cases, right? That's something the makeup lecture will actually go through with you, right? Got to be very careful about exactly how the deletion is done, right? So that's a more sophisticated one you're going to learn about binary search tree, okay? But what I'm going to continue talking about does not depend on this, right? So you should be okay. Just make sure you catch up with the makeup lecture before the exam. Then you should be fine. Okay, so after deletion, and then we are done with the binary search tree lecture. Okay, any question? All right. The last lecture for the course, okay, which we're going to talk about today and also Thursday. We're going to look at priority queues and also heaps and also heap sort. And part of it will also go to the makeup lecture as well, but still within the 90 minutes for that lecture. Okay. Let's now go over a little bit about the basics. So we're going to learn about exactly this one over here, just repeating the point about if you do search on the binary, search tree, worst case linear, best case logarithmic. And high balance property. We're going to define mathematically what we really mean when we say the tree is balanced versus unbalanced. That's something we'll do today. And then we'll talk a little bit about introduction to the abstract data type called priority queue, which is kind of interesting. Okay. And we can see in the beginning on Thursday how we can use like a linked list to really implement priority queue. That will be some naive implementation. However, the very standard implementation, like an efficient one, to implement priority queue is using something called heap. We also going to talk about it. And then after talking about heap, we'll talk about heap sort. So that'll be the last sorting algorithm for this course. Okay, we'll go one step at a time. All right, let's talk about balanced binary search tree. And we already spoke about before the maximum heights will be just linear to the number of nodes. Okay, let's see one more exercise here. Okay, so for this one here, I'm going to do one of them with you, but the other 2 exercise for you. Okay, I'll tell you exactly what you should do. So for example 2 and 3, so these are the exercises for you. And as you try to do them, you want to think about what's the resulting tree's heights. Are they linear or are they logarithmic? Okay, that's the reflection question for you. Okay, but let's now do the first one together. So we kind of start with empty binary search tree. And then we try to insert into the tree one by one. Insert 100 first, and 75, and then 68, 60, and etc. And let's see what the resulting tree will look like. This one kind of tells you this more realistic simulation about what's going to happen in reality. You don't necessarily know all the nodes at one go. You might just go gradually about expanding your tree, in which case you have no control over how the tree is going to look like. Okay. Let's now take a look. So I start with 100. I'll start with empty tree, of course, right? If I insert 100, of course I got 100. And if I got 75, where should it go? It's a binary search tree. Should it go to the left or right? Left, right? Thank you. Straightforward. And what about 68? Left, left, right? And 60, right here. 50, right here. And 1, right here. By the way, this is a binary search tree. Can you see that? Because if you do the in order traversal, it's going to be 1, 50, 60, 68, 75, 100. Sorted. It's a binary search tree. It's just that the height is linear. Okay, if you look at right here, the height is exactly equal to 5, right? You can see 1, 2, 3, 4, 5. Big O of n. It's a linear heights binary search tree, Meaning that if you try to do search, what's the worst case? Linear. No better than linear search. You can do the other two exercises and see how it can result in a tree either with like a linear height or logarithmic height. That's something you can take a look. Okay, so this is just to warm up, to kind of tell you, if you try to do some insertion or deletion without any regulation or fix, then you might just end up with something very bad. Okay, I'll write down the conclusion here. So binary search tree with big O of n heights. That means the search, insertion, and also deletion can be just big O of n. Right? That's a very important conclusion from here. Okay? Cannot be log n. All right, let's now go on to the next one. Now we're going to define mathematically what we really meant for a binary tree or binary search tree to be balanced. Okay? So the one I'm going to talk about is right here. So slide number 4. And this is just a recall about the definition for the height of the tree. We're going to do an example, but you can review this, revisit this definition. And it's something called height balance property. Let's read the textual description first, and we'll see how to apply that into the example. So it's like a recursive property for every internal node in the tree. In order to satisfy this height balance property, we want to make sure the heights of the child nodes, in this case left child and right child, compare their heights. And we want to make sure their heights differ no more than 1. That's the mathematical definition. Let's see exactly how we check it. Okay. All right. So this is the definition, right? You can take a look, but let's now apply that. Let's now focus on just this tree over here. Okay. So we're asking the question, is this tree over here a balanced BST? Does this satisfy the high balance property? Okay. Let's now take a look. Focus. Okay. We start with bottom up. We start with the external nodes. By definition, external nodes has the height 0. So you can simply annotate 0 right here. All right. And then you got to work bottom up. For example, what would be the heights for 51 here? It would be the maximum heights of its children, which is 0, plus 1, which is 1. What is the height for this one here? 2, because maximum heights for its children is 0 and 1, should be maximum 1. Plus 1, 2. All right? Hopefully you got it. What about the height here? 1, right? Maximum of these will be 0 plus 1, it will be 1. What about the height here? 3, right? Maximum here will be 2 plus 1, 3. Right? When you are doing this visually, it doesn't matter the order. You can just do left or right. Doesn't matter, right? As long as you're building up logically. Right? And then 0, 0 maximum plus 1, that'll be give you 1. And 0, 0 plus 1, you'll give you 1. And here maximum of 1 here will be 1 plus 1, that'll be 2. Right? Finally, 2 and 3 maximum is 3 plus 1, give you 4. Right? So this is just to annotate the heights for every node. And now we can check for height balance property. I'll do 2 examples for you. Okay? You can do the rest. Let's see, as far as this particular, as far as this particular internal node is concerned. This one here. That one there has the 2 child nodes, 1 and 1. According to the height balance property, the absolute value of 1 here minus 1 here should be less than or equal to 1. It is, which is good. Okay. Let's see another one here. And then as far as, let's say, this tree is concerned over here, that one there you can see the heights of the children is right here. So 0 less than 0, also less than or equal to 1. All good. So if you check this high balance property for every internal node, all satisfied. So that's why the current tree over here is a balanced binary tree. Okay? But let's see one example where it's not balanced. So that's why the second question here, right? Let's say we take the same tree and put it here, the same tree. We know that it's already balanced. But we say that we want to insert 55. Okay? So if you try to insert 55, so larger than 44, less than 56, larger than 48, larger than 51. So it should really go here, right? Okay? So what we do is we're going to put this one here is going to be 55. Underneath it, we got 2 external nodes. That's the tree after insertion. Is this tree still balanced? We're going to check. Okay? So to check it, we can start with the impacted subtree. That might be easier for us to identify. As soon as we identify any violation scenario for the high balance property, we can stop. Okay? So let's do something similar. We got 0, 0 here. And then maximum of 0 plus 1 will be 1. Okay? And also we got 0 over here. Maximum of 0 and 1 will be 1 plus 1, 2. And this one here is also 0. 0 and 2, maximum is 2 plus 1, 3. Can you spot any violation already? All right. So now, as far as this particular internal node is concerned, as you can see, these 2 child nodes over here have the height difference 0 minus 2. Is it less than or equal to 1? No. So that's a violation. Of the height balance property. That one tells you the log n search running time not guaranteed anymore. All right, that's important. All right, and you guys can do this question here as exercise, okay, right here. What about inserting 63? You can use this diagram here, do the exercise, okay? All right, we got about 4 minutes. Let me just do some very quick introduction about priority queue, and then we are done for today. Just bear with me, about 4 minutes. Okay, okay, let's now go on to priority queue. So priority queue, basically a collection of entries. And just we know what an entry is. It contains a key and a value. But the key difference here is the key in the priority queue does not need to be unique. It's okay to have duplicates. That's an important difference here. Okay, let's now do some quick introduction. Okay, right here. Oh, sorry. There we go. Okay, just several points to mention. Okay, so if you look at each entry here, we got key and value. Key and the value. All right. So we got a priority here. The key denotes the priority. Okay. What I will do is over here. Give me just one moment. Yeah. So for example, you can see the 1 over here is a key value. So the key denotes priority. And here's a principle. The lower the key value, the higher the priority. Okay? If the key value is lower, that means the priority is higher. Okay? That's the convention we are adopting. So that means over here you can see that this one here is the highest priority. On the other hand, you can see that the 9 here is the lowest priority. And also, you can see that we may have duplicates of the priority, in which case these entries are considered as almost equivalent. It doesn't matter which you kind of retrieve first. They're equally urgent. Okay, so these two are entries with the same priority. And does not really matter which one we retrieve. Which entry is retrieved or chosen, doesn't matter. All right, and then two more things. Okay, so here we talk about remove. Whenever you want to remove something from the priority queue, you want to remove the one that's with the highest priority or lowest key value. Remove the entry with the highest priority. Okay, give me 2 more minutes and then we're done. Okay, so that's a very like a quick summary about priority queue. We're going to see on Thursday how we can implement it. But let me do a final comparison. I want you guys to compare the priority queue with the FIFO queue. Do you guys remember what FIFO stands for? First in, first out? Okay, awesome. Okay, let's do that quickly. Okay, only take 1 minute. So first of all, entries removed from priority queue are according to the priorities, of course, key value. On the other hand, the entries that we actually remove from the FIFO queue according to what order? First in, first out, right? The fancy term for that is something called chronological order, right? Depending on the timing, okay? Okay, let me write it down. Chronological order. Okay, very quick highlights. For FIFO queue, chronological order. And then for priority queue, it's about key values. All right, so on Thursday will be the last class. Make sure you come. I'll talk a little bit more about the exam, a little bit in the beginning. And then we'll also continue with some discussion about heap and heap sort. All right, see you on Thursday.